By one influential estimate, the observable universe may contain roughly 2 trillion galaxies, with planets now understood to be at least as common as stars. Let that sit for a moment, not as a statistic, as a reality. 2 trillion galaxies, each one containing hundreds of billions of stars. Each star orbited on average by at least one world. The math, when you actually do it, produces a number so large that every notation system humans have invented struggles to write it cleanly. The number of worlds that exist, or have existed, or will exist within the boundaries of what light has had time to reach us since the beginning of everything, is not merely astronomical. It is a number that makes the word astronomical feel insufficient. And across all of it, in every direction, at every wavelength, from every corner of that almost incomprehensible expanse, we have heard one thing: silence. Not static, not the background hiss of a universe doing its ordinary physical business, which we hear plenty of. Silence, in the specific sense that matters here. No pattern, no repetition, no signal shaped by intention, no voice, no evidence. In 75 years of the most sophisticated listening our species has ever done, that anywhere in all of that vastness, anything has ever looked up and tried to reach across the dark towards something else that might be listening. Just silence. On a Tuesday afternoon in the summer of 1950, a man named Enrico Fermi sat down to lunch at a cafeteria in Los Alamos, New Mexico. He was there because the United States government had asked him to be, for reasons that were not unrelated to the silence I just described, though Fermi himself would not have connected them that way. He was arguably the greatest experimental physicist of the 20th century. He had built the first nuclear reactor. He had helped design the weapon that changed what it means for a civilization to possess certain kinds of knowledge. At lunch that day, the conversation drifted, the way lunch conversations do, toward a cartoon that had been running in the New Yorker. Something about flying saucers. Fermi's colleagues said what people said about flying saucers in 1950, which is more or less what people say about them now. The conversation moved on. They talked about something else. And then, in the middle of an apparently unrelated discussion, Fermi laughed and asked a question that nobody at the table expected. But where is everybody? His colleagues knew immediately what he meant. Not the flying saucers. The universe. The 2 trillion galaxies. The hundreds of billions of stars per galaxy. The planets. The billions of years the whole enterprise had been running before our own sun had even formed. Given all of that time and all of that space and all of those chances, where was everybody? Why was the sky silent? Why had no one passed through? Why had no signal arrived? Why, in a universe this old and this large and this full of the raw material for worlds, were we apparently alone? The question had no answer in 1950. It has no answer now. What has changed in the 75 years between that lunch table and this moment is not the answer. It is our understanding of how deep the question goes. Because the more carefully you examine the silence, the more you realize that it is not just telling us something about what might or might not be out there. It is telling us something about ourselves, about what it takes for a civilization to survive, about how rare, or how fragile, or how self-defeating intelligence might turn out to be in a universe that has had billions of years to produce it and, as far as we can tell, has produced it exactly once. Maybe the silence is not telling us that no one is out there. Maybe it is telling us something about what happens to civilizations after they learn how to speak. That is the question this story is going to follow. not toward a clean answer, because there is no clean answer, and anyone who offers you one is selling something, but toward the place where the question leads when you follow it honestly, without flinching, all the way to where it actually points, which is not outward, toward the stars. It is inward, toward us. Chapter 1. A universe that should not be empty. There is a calculation that changes you the first time you do it, honestly, not the kind of calculation that requires advanced mathematics or a physics degree or access to equipment that most people will never see. The kind that requires only numbers that are publicly available, a willingness to multiply them together, and the intellectual honesty to sit with what the result actually means rather than immediately reaching for a reason to dismiss it. Start with what we know. The Milky Way contains somewhere between 100 billion and 400 billion stars. The honest number is that we do not know precisely, because counting the stars in your own galaxy is like trying to count the trees in a forest while standing inside it. But the estimates converge around 200 billion as a reasonable working figure. 200 billion stars. In one galaxy, there are, by current estimates, approximately 2 trillion galaxies in the observable universe. The word observable matters here. It does not mean all there is. It means all there is within the distance that light has had time to travel to us since the universe began. The actual universe, if it extends beyond what we can observe, which current cosmological models suggest it almost certainly does, is larger still, possibly infinitely larger. But we will stay with what we can see, because what we can see is already more than sufficient to make the point. 200 billion stars per galaxy. 2 trillion galaxies. The multiplication produces a number in the range of 400 sextillion stars in the observable universe alone. Written out, that is a 4 followed by 23 zeros. There is no intuitive way to feel that number. The human brain was not built to feel numbers that large. It was built to track the movements of animals across a savanna, to remember faces, to calculate whether a thrown stone will hit its target. The part of cognition that handles genuinely astronomical quantities operates more like a label than a feeling. You can write the number down. You cannot hold it. What you can do is work with what it implies. We know now that planets are not rare. This was not always obvious. For most of human history, the question of whether other stars had planets orbiting them was genuinely open. The assumption that they did was reasonable but unconfirmed. That changed in the 1990s, when astronomers developed techniques sensitive enough to detect the gravitational wobble that a planet induces in its star. And then again, when the Kepler Space Telescope spent 4 years staring at a small patch of sky and catalogued thousands of planets in that patch alone by looking for the tiny dimming that occurs when a planet passes in front of its star. The numbers that came back from Kepler and from the missions and surveys that followed it were, depending on your disposition, either wonderful or vertiginous. Astronomers have now confirmed more than 6,000 exoplanets, with thousands more candidates awaiting confirmation. But the confirmed number is not the important number. The important number is the statistical inference from those detections based on what Kepler found. Astronomers estimate that virtually every star in the Milky Way has at least one planet. Some have many. The average appears to be somewhere between 1 and 2 planets per star. And many of those planets fall into the category of rocky worlds, roughly the size of Earth, orbiting at distances that allow for liquid water on their surfaces. Not all of them, not most of them, depending on how strictly you define the habitable zone, but some fraction. A fraction that, multiplied across 200 billion stars, produces a number of potentially habitable worlds in our galaxy alone that runs well into the billions. Billions of potentially habitable worlds in one galaxy of 2 trillion. Now add time. The universe is approximately 13.8 billion years old. Our Sun is approximately 4.6 billion years old, which means that when our Sun formed, the universe had already been running for more than 9 billion years. Stars older than our Sun have been burning steadily for long enough that any planets orbiting them would have had billions of years more than Earth has had to develop whatever they were going to develop. If life appeared on some of those worlds at roughly the same pace it appeared on ours, the civilizations that might have emerged from that life could be billions of years ahead of us. Not thousands, not million, billions. A civilization 1 billion years more advanced than ours is not a civilization we can meaningfully imagine. We can barely imagine 1,000 years more advanced. 1 billion years is a span of time in which anything that physics permits could have been accomplished. Technologies that look like magic from where we stand. The ability to rearrange matter at scales we cannot conceive. Possibly the ability to move between star systems, to colonize galaxies, to leave marks on the universe so large that they would be visible across cosmological distances. And yet, here is where the numbers stop being wonderful and start being strange. In 1960, a young astronomer named Frank Drake sat down and tried to organize the question of whether intelligent life existed elsewhere in the universe into something that could be reasoned about systematically. What he produced was not an answer. It was a framework, an equation, now bearing his name. That breaks the question down into its component parts and asks you to estimate each one separately before multiplying them together to arrive at a guess about how many communicating civilizations might exist in our galaxy at any given time. The Drake equation is not a calculation in the sense that produces a reliable result. It is a calculation in the sense that forces you to be explicit about what you are assuming. Each variable in the equation represents something we either know, can estimate, or are genuinely uncertain about. And working through them in order is an experience that starts with confidence and ends somewhere more uncomfortable. The first variables are the ones we know best. The rate at which new stars form in the Milky Way, the fraction of those stars that have planets, the number of those planets that are potentially habitable. These numbers have gotten sharper over the past 30 years as telescopes and detection methods have improved. And they are broadly reassuring if what you are looking for is reason to believe the universe might be populated. Stars form, planets form around them, habitable worlds are common. Then you reach the variables that are harder, the fraction of habitable worlds on which life actually appears. We have exactly one data point for this Earth. On Earth, life appeared remarkably quickly after the planet cooled enough to support it. Within a few 100 million years of Earth's formation, microbial life was already present. Some researchers take this as evidence that life, once the conditions for it exist, tends to appear rapidly and perhaps inevitably. Others point out that we cannot draw statistical conclusions from a single example if you want to know the probability that a coin comes up heads. Flipping it once and getting heads does not tell you the probability is 100%. It tells you almost nothing. We have flipped the coin of life once, gotten heads, and are now trying to infer the bias of the coin from that single result. It cannot be done. Not rigorously. Not honestly. What we can say is that the emergence of life on Earth required liquid water, a source of energy, and certain organic chemistry. All three of those things appear to be common in the universe. Whether their combination reliably produces life, or whether life is a freakish accident that the universe has pulled off exactly once, is a question that every honest scientist working on this problem will tell you remains genuinely open. But assume, for the sake of following the equation forward, that life does appear on some fraction of habitable worlds, a generous fraction, say 1%. 1% of the billions of habitable worlds in the Milky Way is still tens of millions of worlds with life. The number remains enormous. Then comes the variable that the equation calls the fraction of life-bearing worlds on which intelligence evolves. And here the equation begins to feel less like a calculation and more like a mirror held up to our assumptions. We assume, without always examining the assumption, that intelligence is the natural destination of evolution. That, given enough time and enough selection pressure, life will tend toward complexity. And complexity will tend toward brains. And brains will tend toward the kind of cognition that builds tools and asks questions and eventually builds radio telescopes. This assumption is so deeply embedded in how we think about the question that most discussions of the Drake equation treat the variable for intelligence as though it were close to 1. As though, of course, intelligent life follows from life the way day follows night. Life has existed on Earth for approximately 3.8 billion years. For the overwhelming majority of that time, it was microbial, single cells, bacteria, archaea, simple organisms doing what simple organisms do, dividing and metabolizing and competing for resources in ways that were extraordinarily successful. Bacteria did not need brains. They did not need nervous systems or language or the capacity for abstract reasoning. They needed to eat and reproduce. And they were phenomenally good at it. They still are. By mass, by number, by metabolic influence on the planet, bacteria remain the dominant form of life on Earth. We are the anomaly, not them. Complex multicellular life, the kind that produces animals with nervous systems, and eventually the particular configuration of nervous system that generates what we call intelligence, appeared only about 600 million years ago. That is a long time in human terms. It is a small fraction of the time life has existed on Earth. And in those 600 million years, exactly one lineage has produced a species capable of asking whether it is alone in the universe. One out of millions of species, over 600 million years. Intelligence, it turns out, is not what evolution is trying to make. Evolution is not trying to make anything. It is a process without direction or intention, producing whatever survives long enough to reproduce. Bacteria survive. They have been surviving for nearly 4 billion years. Sharks have been surviving for 450 million years. Crocodilians have been surviving for 240 million years. None of them need intelligence. None of them are trending toward it. They found strategies that work, and they kept using them. Because that is what selection does. Intelligence is one strategy, a costly one. As it happens, the human brain consumes roughly 20% of our caloric intake, while constituting roughly 2% of our body weight. That is an extraordinary metabolic investment for a single organ. Evolution does not make those investments unless they pay off in reproductive terms. And for most of the history of life on Earth, the return on the intelligence investment was not sufficient to drive the lineage toward it. What changed? Eventually, for our particular lineage, is a set of circumstances so specific and so contingent that reproducing them elsewhere in the universe is not guaranteed, not even, perhaps, likely. But assume again, for the sake of following the equation, that intelligence does emerge on some fraction of life-bearing worlds, a smaller fraction this time, maybe 1 in 1,000, maybe 1 in a million. Even at 1 in a million, the residual number of intelligent civilizations in the Milky Way remains in the thousands. Thousands of civilizations in one galaxy that we should, by this point in the calculation, expect to find evidence of. And then comes the last variable, the one that changes everything. Drake called it L. It is the average length of time that a communicating civilization remains detectable. How long? Once a civilization develops the technology to send signals into space, does it continue to do so? How long does it survive? L is the variable for which we have exactly one data point. Us. We have been a communicating civilization, in the sense of leaking detectable electromagnetic signals into space, for roughly 100 years. Radio, television, radar, the bubble of signals we have broadcast, traveling outward at the speed of light, is now approximately 100 light-years in radius. In a galaxy, 100,000 light-years across. That bubble is a speck. 100 years. That is how long we have been. In this specific sense, findable, whether we will be findable for another 100 years, or another 1,000, or another million, is a question that depends on things that are not, in any way, guaranteed. It depends on whether we solve the problems that our own technology has created. It depends on whether the intelligence that built the radio telescope can also manage what the radio telescope and everything else we have built has made possible to destroy. That is the variable L. And it is the variable that, more than any other in the Drake equation, turns the question of the Fermi paradox from a question about the universe into a question about us. Because here is what the equation, when you run it honestly, produces. If L is large, if civilizations tend to survive for millions of years once they develop technology, then the Milky Way should be full of them. There should be signals everywhere. There should be evidence of engineering on astronomical scales. There should be something detectable, something unmistakable, something that 75 years of searching would have found by now. And there is nothing, which means either the earlier variables in the equation are far smaller than they appear, or L is very small indeed, or something else is happening that we have not yet understood. None of those options are comfortable. The silence is not a neutral fact. It is data. And when you hold it against the numbers that say the universe should not be silent, you are left with a contradiction that cannot be resolved by assuming the answer is simple. Something is wrong with our expectations, or something is wrong with civilizations. The question the rest of this story will follow is which one? Chapter 2. The Ladder of Miracles. There is a question that sounds simple until you actually try to answer it. What had to happen, exactly, for you to exist? Not in the personal sense of parents and circumstances, and the specific chain of events that produced your particular life. In the deeper sense, the biological sense, the chemical and geological and astronomical sense. If you trace the sequence of events that had to occur, in the right order, at the right time, with the right outcomes, for a universe of hydrogen and helium and a few heavier elements to eventually produce a creature capable of asking where everybody is. You get a list that does not get shorter. The more carefully you examine it, it gets longer. And each item on the list, when you look at it closely, turns out to be not a certainty, but a contingency. Not something that had to happen, but something that happened, and that might not have, and that we have exactly one confirmed example of having happened anywhere in the observable universe. That list is what this chapter is about, not as a celebration, not as an argument for cosmic specialness or divine design, or any conclusion that the science does not actually support, as a sober accounting of what the silence might be telling us. Because if any of the steps on this ladder are genuinely rare, genuinely improbable, genuinely difficult in a way that most places in the universe cannot replicate, then the silence has an explanation that does not require civilizations to be destroying themselves. It requires only that getting started is harder than it looks. Start at the beginning. The very beginning. The universe is approximately 13.8 billion years old and began, as far as current physics can determine, in a state of extraordinary density and temperature that expanded rapidly into what we observe today. The first atoms were hydrogen and helium. The first stars were enormous, burning fast and hot, and seeding the universe with heavier elements when they died in explosions, powerful enough to forge iron and carbon and oxygen and the rest of the periodic table in their final moments. Those heavier elements scattered into the interstellar medium. Subsequent generations of stars formed from clouds that contained them. Planets formed from the debris left over when those clouds collapsed. This process took time. A lot of it. The universe had to run through several generations of stellar birth and death before the raw material for rocky planets rich in heavy elements was sufficiently abundant. Our solar system, forming approximately 4.6 billion years ago, was a beneficiary of all that prior stellar processing. The carbon in your body was forged in the heart of a star that died before our sun was born. The iron in your blood was made in a supernova. You are, in the most literal chemical sense, the product of previous stars. This is a beautiful fact. It is also a fact that has a timing implication that matters for the Fermi paradox. The universe could not have produced Earth-like planets much earlier than it did, because the heavy elements required for rocky worlds and for biochemistry were not yet sufficiently abundant. The window for complex life has been open for perhaps the last 8 or 9 billion years. That is a long time. Long enough that civilizations far older than ours are possible, but it is not an infinite window. And the earliest possible civilizations are constrained by the same stellar chemistry that constrained us. Now, land on the early Earth. 4 billion years ago. A world nothing like the one that exists today. No oxygen in the atmosphere. Constant bombardment from the debris left over from planetary formation. Oceans of liquid water. Yes, but oceans that were chemically nothing like the oceans of the modern world. A world that was, by any standard we would apply today, hostile to the kind of life we are familiar with. And yet, life appeared, not quickly by human standards, not overnight, but quickly by geological standards, which is the only relevant measuring stick for a process playing out over billions of years. The earliest evidence for microbial life on Earth dates to approximately 3.7 to 3.8 billion years ago. Only a few 100 million years after the planet had cooled enough to support liquid water consistently. In the context of Earth's history, that is fast. Fast enough that some researchers have argued it suggests life, once the right conditions exist, appears almost inevitably. But here is the thing about that argument. We do not know how life first appeared on Earth. This is not a gap that is about to be closed. The origin of life, the transition from chemistry to biology, from self-replicating molecules to the first entities that can reasonably be called alive, is one of the most profound unsolved problems in all of science. We have hypotheses. Some of them are plausible and supported by experimental evidence. The idea that life originated near hydrothermal vents on the ocean floor, where chemistry and heat and mineral surfaces might have catalyzed the first self-replicating molecules, is a hypothesis with genuine scientific traction. The idea that organic molecules arrived from space, delivered by comets or asteroids, and contributed to the chemical inventory that eventually produced life, is also supported by the detection of amino acids and other organic compounds in meteorites. What we do not have is a confirmed mechanism, a step-by-step account of how the first living thing assembled itself from non-living chemistry, tested against experiment, and confirmed to actually work. We have the beginning of the story, which is a universe full of chemistry, and the end of the story, which is life on Earth. The middle is still missing, and the middle matters enormously for the Fermi paradox. Because if the middle is easy, if the chemistry to life transition happens readily, given the right conditions and enough time, then life is probably common in the universe. If the middle is hard, if it required a specific and improbable sequence of chemical accidents that might not be reproducible most of the time, even given identical starting conditions, then life might be rare. Rare enough that the silence makes sense without requiring anything further. We do not know which it is. What we can say is this: the conditions that preceded the origin of life on Earth appear to be common in the universe. Liquid water exists on multiple worlds in our own solar system, and on statistically vast numbers of worlds elsewhere. Organic chemistry is not exotic. Carbon compounds are found throughout the interstellar medium, in comets, in meteorites, in the atmospheres of gas giants. The raw ingredients for biochemistry are not the bottleneck. As far as we can tell, whether the assembly process itself is the bottleneck is the question that remains open. But suppose life does appear. Suppose the chemistry to biology transition, however it works, happens on some fraction of the worlds where conditions permit it. What comes next? For the first 2 billion years of life on Earth, not much. Or rather, not much that would have been visible from a distance. The Earth was covered in microbial life, bacterial mats, single-celled organisms metabolizing, reproducing, competing, evolving, extraordinarily successful by any biological measure, completely invisible to any civilization that might have been scanning our solar system from a neighboring star, looking for signs of technology. 2 billion years of microbial life, and then another step that turns out to be, in its own way, as improbable as the first. The emergence of the eukaryotic cell. A eukaryotic cell is fundamentally different from a bacterial cell in a way that goes far beyond size or complexity. At its core, the eukaryotic cell contains within it the remnants of what were once separate organisms, mitochondria, the structures that power the cell by converting nutrients into usable energy, are the evolutionary descendants of bacteria that were engulfed by another cell approximately 2 billion years ago and never left. Instead of being digested, they were domesticated. They gave up their independent existence and became permanent residents, providing energy in exchange for protection and resources. This event, which biologists call endosymbiosis, happened once. As far as we can determine from the genetic evidence, every eukaryotic cell on Earth, every cell in your body, every cell in every animal and plant and fungus that has ever lived, descended from a single ancestral merger between two cells that happened approximately 2 billion years ago. Every complex organism on Earth traces its existence to one specific event in one specific ancient ocean. Once, in 2 billion years of life on Earth, the paleontologist Andrew Knoll, who has spent his career reading the history of early life in ancient rocks, has described this transition as one of the most difficult steps in the history of life. Not impossible, clearly, since it happened, but the fact that it happened only once in 2 billion years of opportunity suggests that it is not easy, not something that happens routinely given the right conditions, something that required a specific convergence of circumstances that, across 2 billion years of bacterial life on a planet covered in potential hosts and potential symbionts, occurred exactly one time, and from that one time, everything complex that has ever lived on Earth descended. Now go further up the ladder. Multicellular life. Organisms made of many cells working together. Each cell specialized for a particular function, coordinated by chemical signals and genetic programming into a coherent whole. Sponges, jellyfish, worms, fish, everything visible to the naked eye that has ever lived on this planet. All of it descended from single-celled ancestors that, at some point, began sticking together and differentiating rather than simply dividing into independent copies. Multicellularity evolved independently multiple times in the history of life on Earth. In animals, in plants, in fungi, in algae, in several other lineages. In that sense, it appears less rare than endosymbiosis. But the kind of multicellularity that produces complex animals, with tissues and organs and coordinated behavior, and eventually the nervous systems that make intelligence possible, appears to have a narrower origin. The lineage leading to complex animals traces back to a common ancestor that lived approximately 600 million years ago. 600 million years ago. In the context of Earth's 4 billion year history, is recent. Life had been on this planet for more than 3 billion years before the ancestors of animals existed. 3 billion years of opportunity to produce complexity, during which the most complex things alive were colonial microbial mats and the occasional simple multicellular organism. Whatever it was that allowed the animal lineage to emerge when it did, the confluence of oxygen levels rising in the atmosphere after billions of years of photosynthesis, the end of the last major global glaciation, a set of ecological opportunities that had not previously existed. It was not something that the previous 3 billion years had managed to produce. 3 billion years. And then, in a geologically brief window, complex animals now go to the step that feels most relevant to the Fermi paradox, the one that seems most obviously necessary for a civilization to exist, the evolution of intelligence. And here is something that most discussions of this topic avoid saying clearly. Intelligence, in the specific sense we mean when we ask whether intelligent life exists elsewhere, is not a destination. It is not what evolution is pointing toward. It is not the peak of a mountain that all life, given enough time, will eventually climb. It is one solution to one set of problems in one environment that one lineage happened to arrive at through a specific and unrepeatable sequence of evolutionary events. Consider what intelligence actually is. Biologically, it is a large, energetically expensive brain capable of flexible behavior, abstract reasoning, language, and the transmission of learned knowledge across generations. It is useful in certain ecological contexts, an environment with complex social dynamics, varied food sources, unpredictable challenges, a premium on behavioral flexibility over fixed instinct. Those are conditions that can favor the evolution of increasingly sophisticated cognition. But those are not universal conditions. And even in environments where they exist, intelligence is not the only solution. Wolves and ravens operate in complex social environments without evolving human-level cognition. Dolphins and elephants have large brains and sophisticated social lives and have not built radio telescopes. The lineage that produced us arrived at our particular configuration of intelligence through a series of evolutionary events. the development of bipedalism that freed the hands for tool use, the expansion of the social group that created pressure for more sophisticated communication, the dietary shifts that made it energetically possible to support a larger brain, none of which were inevitable from where they started. Sharks have been largely unchanged for 450 million years. Crocodilians have been largely unchanged for 240 million years. Horseshoe crabs have been largely unchanged for 450 million years. These are not failures. They are extraordinary successes. They found a way to survive, and they kept doing it. Because survival is what evolution selects for, not sophistication. The universe may not be empty of life. It may be full of worlds that breathe and divide and swim and crawl and bloom, covering their oceans with microbial mats and their shallow seas with the descendants of simple animals that never needed to ask where everybody was. Because asking questions was never part of the strategy that kept them alive. A world of bacteria is not a world that has failed to produce intelligence. It is a world that has succeeded at being what it is. The silence of that world is not evidence of absence. It is evidence of a different kind of presence, one that has no reason to transmit and no capacity to receive, and that is therefore invisible to any civilization listening for the particular kind of signal that only a particular kind of mind would think to send. This is the first rung of the ladder where the silence might find its explanation, not in destruction, not in barriers, simply in the fact that the steps required to go from hydrogen and helium to a species capable of building a radio telescope are numerous and contingent, and each one a smaller miracle than it appears from the inside, where we mistake our own existence for evidence. That existence of this kind is easy. It is not easy. The evidence for that is everywhere. If you know how to look for it, it is in the 3.8 billion years of microbial life before the first animal. It is in the single endosymbiotic event that gave rise to every complex cell on Earth. It is in the 600 million years between the first animals and the first civilization. It is in the hundreds of millions of species that have lived and died on this planet, the overwhelming majority of which were not trending toward intelligence, were not moving up any ladder, were simply doing what worked until the conditions changed and something else did. We are at the top of a ladder that most worlds, perhaps most worlds in the universe, never climb past the first few rungs. That is one answer to the silence. But it is not the only answer, and it is not the most important one, because even if intelligence is rare, the numbers suggest it should have appeared somewhere. Many times, in billions of years of cosmic history, across hundreds of billions of galaxies, the improbable becomes likely often enough that complete silence is hard to explain by rarity alone, which means we have to climb further, past the question of how hard it is to produce intelligence, and into the question of what intelligence does once it exists. And that is where the story gets considerably darker. Chapter 3. The Great Silence. In the spring of 1960, a 29-year-old astronomer named Frank Drake drove to a radio telescope in the mountains of West Virginia and did something that no human being had ever done before. He listened, not casually, not the way you might tilt your head toward a sound you think you heard in another room. Deliberately, systematically, with a purpose that he had thought about carefully enough to give it a name. He called it Project Ozma, after the queen of a fictional land that was very far away and very hard to reach. He pointed the 85-foot dish of the Green Bank telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, each within 12 light-years of Earth. He tuned the receiver to a frequency of 1,420 megahertz, a frequency that made physical sense as a universal channel for communication, because it is the emission frequency of neutral hydrogen, the most abundant element in the universe. And any civilization with a working knowledge of chemistry would know it. He sat down. He waited. And the universe, for 6 hours on that first morning and for the weeks that followed, said nothing. Drake was not discouraged. He had not expected to find anything in the first attempt. He was not even sure, at that point, that the question had a definitive answer. What he was sure of was that the question deserved to be asked seriously, with real equipment and real methodology, rather than dismissed as the kind of thing that serious scientists did not bother with. That conviction that the search was worth conducting even without any guarantee of a result became the foundation of something larger. In November of the same year, Drake gathered a small group of scientists at Green Bank for what is now recognized as the first formal scientific meeting on the search for extraterrestrial intelligence. 11 people attended. Among them were Carl Sagan, then a young researcher at the beginning of a career that would make him the most recognizable science communicator of his generation. And at the beginning of the meeting, Drake wrote an equation on the blackboard, not a solution, a framework, a way of organizing the question into its component uncertainties so that they could be discussed and estimated separately. The equation that Drake wrote that morning in Green Bank is the same one introduced in the previous chapter. It was not derived from data. It was derived from the structure of the problem itself, from the observation that the number of communicating civilizations in the galaxy at any given time must depend on a sequence of factors that could, in principle, be estimated even if they could not yet be measured. Drake did not know, on that morning, that the equation he wrote on the blackboard would still be the organizing framework for this question 65 years later. He did not know that the search he was beginning would expand into a global scientific enterprise involving multiple observatories, hundreds of researchers, and billions of computational operations performed by volunteers on personal computers around the world. He did not know any of that. He just wrote the equation and listened. That spirit of listening, serious and sustained and undiscouraged by silence, is what defines the 65 years that followed. And before we go further into what the silence might mean, it is worth spending time inside that listening itself, not as a technical exercise, but as a human one. Because the people who built their careers around this search were not doing what they were doing out of naivety or wishful thinking. They were doing it because they understood, perhaps better than anyone, what a positive result would mean, not just for science, for everything. Consider Jill Tarter. Tarter is perhaps the most significant figure in the history of this search after Drake himself. She joined the effort in the 1970s, when it was still regarded by most of the scientific establishment as a fringe pursuit, and she devoted the next 4 decades to it, with a focus and persistence that became, in itself, a kind of argument for the importance of the question. She led the development of increasingly sophisticated signal detection systems. She helped build the institutional infrastructure that transformed the search from a collection of individual efforts into something resembling a coordinated scientific program. She became the face of the search for a generation of scientists and the public alike. When Tarter spoke about the search after her retirement, she returned repeatedly to a specific image. She compared the total volume of space that the search had examined, across all its programs and all its years, to a single glass of water taken from Earth's oceans. In terms of the range of frequencies examined, the directions surveyed, the distances probed, and the types of signals sought, everything humanity had done to listen for extraterrestrial intelligence amounted to taking one glass of water and looking for fish in it. Then concluding from the absence of fish in that glass that the ocean had no fish. It is a compelling image. It argues for humility about what the silence proves. It argues that we have not searched enough, not with enough sensitivity, not across enough frequencies, not in enough directions, to draw confident conclusions from the silence. She is right about the limitations of the search, and the silence, even given those limitations, is telling us something. Here is why. The argument that we have not searched enough applies most forcefully to weak signals, distant source, and unconventional transmission methods. It is a strong argument against concluding that there are no civilizations anywhere in the universe broadcasting at low power on radio frequencies we have sampled. It is a weaker argument against the absence of something else, something that the search has not found evidence of, even though it would not require extremely sensitive detection. A civilization 1 million years more advanced than ours, assuming it survived that long, would have had time to do things that would be visible across the galaxy without any need for a targeted transmission. The physicist Freeman Dyson proposed in 1960 that a sufficiently advanced civilization would eventually build a structure that captured all the energy output of its star. Such a structure would be visible as an infrared anomaly even from very large distances. We have not found one, not a confirmed one. The galaxy, as far as we can tell from a century of increasingly sensitive observation, does not appear to have been modified by engineering on astronomical scales. There are no obvious signs of resource extraction from multiple star systems, no structures visible in infrared surveys that suggest the energy harvesting of a mature civilization, no patterns in stellar distributions that look like deliberate arrangement, no signals in any frequency range that have withstood scrutiny as artificial. Absence of evidence is not evidence of absence, as the saying goes, but the saying is often used as though it means absence of evidence is meaningless. It does not mean that absence of evidence, when you have looked carefully enough and long enough, shifts the probabilities. The more carefully you look and the less you find, the more the absence tells you. We have looked imperfectly, incompletely, with instruments that are limited in ways we understand, and possibly in ways we do not yet understand. And we have found nothing that has survived peer review as a confirmed signal of extraterrestrial intelligence. It is in this context, against this backdrop of decades of careful and ultimately unrewarded listening, that one evening stands apart from all the rest. August 15th, 1977. Jerry Amon was not at the telescope when it happened. He was sitting at his kitchen table a few days later, reviewing the printout from a survey that the Big Ear Radio Telescope at Ohio State University had been conducting as part of an ongoing program. The printout was columns of alphanumeric characters representing signal intensity, the kind of output that looks like noise until you know what you are looking at. Most of it was noise, background hiss, interference, the ordinary electromagnetic conversation of a universe doing its physical business. And then, in the middle of a column, Amon saw something that was not noise, a sequence of characters representing a signal so strong, so narrowband, so consistent with what a deliberate transmission from space would look like, that Amon circled it with a red pen and wrote a single word in the margin. Wow! The signal lasted 72 seconds, which was how long it took the rotating Earth to carry the telescope's field of view past whatever the source was. It was detected at a frequency close to the hydrogen line, which is exactly where decades of theoretical work had predicted a deliberate transmission would most likely be found. Its intensity was roughly 30 times stronger than the background noise. It had exactly the characteristics that researchers had argued a genuine alien signal would have, and it was never detected again. Not for lack of trying. The Big Ear telescope returned to that patch of sky more than 50 times in the years that followed. Other telescopes around the world pointed at the same coordinates. The most sensitive instruments available were trained on the source. Nothing. The signal that Eamon circled in red ink in his kitchen in 1977 remains, to this day, the most credible candidate for an extraterrestrial transmission ever detected. And it remains still without a widely accepted explanation. Not confirmed as extraterrestrial, not explained as a natural phenomenon. A single data point that is consistent with what the search was looking for, and that has not repeated, which is exactly the kind of ambiguous, maddening evidence that this question seems to specialize in producing. Eamon himself has maintained for decades the only intellectually honest position available. We do not know what it was. What we do know is this. After 65 years of listening, across every frequency and every direction it has examined, the most sophisticated search our species has ever conducted has returned the same thing. Silence. That silence is not proof of anything by itself. It is not proof that we are alone. It is not proof that civilizations are rare. It is not proof that something destroys every civilization before it becomes detectable. But it is data. And when you hold that data against the numbers from the previous chapters, when you hold 65 years of silence against a galaxy that should, by reasonable estimates, contain thousands of civilizations, if the optimistic variables in the Drake equation are correct, you arrive at a tension that cannot be resolved by assuming everything is fine. Something, somewhere, is not adding up. The universe should not be this quiet, and the question of why it is, the question that Fermi asked at a lunch table in 1950, and that nobody has answered since, turns out to have a set of possible explanations that range from reassuring to deeply unsettling. Most of them are unsettling. The most unsettling of all has a name, and it begins not with a question about the universe, but with a question about us. Chapter 4. The Great Filter. In the summer of 1998, an economist at George Mason University named Robin Hanson published a short paper with a title that sounds more like a philosophical puzzle than a scientific argument. The paper was called The Great Filter, Are We Almost Past It? It was not long. It was not filled with equations or experimental data or the apparatus of formal scientific publication. It was a piece of reasoning, careful and relentless, that started from a simple observation and followed it to a conclusion that, once you understand it fully, is one of the most disturbing things a person can sit with. The observation was this: the universe is old. It is large. It contains an enormous number of stars and planets. The raw material for life and for intelligence is widely distributed. Given all of that, if the emergence of civilization were not extraordinarily difficult, the galaxy should be full of civilizations, many of them billions of years older than ours. And yet, as we established in the previous chapter, the galaxy appears to be empty of detectable intelligence. Something is filtering them out, not a conspiracy, not a weapon, not an external force that hunts civilizations down. A probability, a step in the sequence from dead matter to interstellar civilization that is so difficult, so improbably, so close to impossible, that almost nothing makes it through. A bottleneck so severe that a universe full of the right raw material produces, in practice, almost no civilizations that survive long enough to become visible across interstellar distances. Hansen called this the great filter. And the argument he made about it is worth following carefully, because it leads somewhere that most people, when they first encounter it, do not expect to go. The sequence from dead matter to interstellar civilization can be broken into steps. The formation of a habitable planet, the emergence of life, the development of complex cells, the emergence of multicellular organisms, the evolution of intelligence, the development of technology, the survival of a technological civilization long enough to expand beyond its home world. Each step must succeed for the next one to become possible. Each step that succeeds narrows the path for everything that follows. Somewhere in that sequence, Hansen argued, there is a step that almost nothing survives. We can call it the filter because that is what it does. It takes the vast number of worlds that could, in principle, produce interstellar civilizations and reduces them to something close to zero. The terrifying question, the one that Hansen placed at the center of his paper and that has not been resolved in the 27 years since, is this: is the filter behind us, or is it ahead? Those are the only two possibilities. Either the step that almost nothing survives is somewhere in our past, in the sequence of events that produced us, or it is somewhere in our future, in the sequence of events that a civilization must navigate after reaching our current stage. And the difference between those two possibilities is not academic. It is the difference between two entirely different pictures of what we are and what our future might hold. Let me take you through each one. If the filter is behind us, it means that one or more of the steps that led to our existence were extraordinarily rare. The emergence of life from chemistry, the development of complex cells, the evolution of intelligence. Some step in our past was so improbable that almost no other world has made it through, which is why the galaxy appears empty. We are here because we beat odds that were almost insuperably long. We are a statistical miracle. And if we are a statistical miracle, then the silence is explained. Not by destruction, by rarity. The universe is not full of civilizations that have been destroyed. It is mostly empty of civilizations that ever formed. If this is the case, then we are, or very nearly are, alone. The silence is not a warning. It is the natural condition of a universe that is extraordinarily good at producing the prerequisites for complexity and extraordinarily bad at actually producing it. We are an accident, in the most profound sense of that word, an outcome that the universe was not aiming for, and that is almost certainly not repeated anywhere within the range of what we can observe. That is a strange kind of comfort. Strange because it is not what most people mean by comfort, being told that you are alone in the universe, but there is something in it that is, at least, not frightening in the immediate and personal sense. If the filter is behind us, our future is, in principle, open. There is no barrier ahead. The silence is not a prophecy about what happens to civilizations like ours. It is a testament to how difficult it was to become a civilization like ours. We made it through something almost nothing makes it through. That is one possibility. Now consider the other. If the filter is ahead of us, it means that the steps behind us, the emergence of life, the evolution of complexity, the development of intelligence and technology, are not the rare part. They are the easy part. Civilizations like ours are not statistical miracles. They are, perhaps, common. Many worlds have produced them. Many worlds have reached the point we are at now. A technological civilization capable of transmitting signals into space, capable of contemplating its own existence and the existence of others, capable of wondering where everybody is, and then something happens. something that almost all of them cannot survive. Not an external threat, not an asteroid or a stellar flare or a passing gamma-ray burst. Though those things exist and occasionally destroy worlds, something internal, something that arises from within the civilization itself, from the same intelligence and technology that made it capable of asking the question in the first place, because here is what the filter ahead hypothesis requires. It requires that at some stage in the development of a technological civilization, there is a threshold that almost none of them cross successfully. A challenge that the intelligence which carried them to that threshold is not, by itself, sufficient to navigate. Something for which being smart enough to build the technology is not the same as being wise enough to survive having it. In the summer of 1945, in the desert of New Mexico, a group of scientists detonated the first nuclear weapon. The test was called Trinity. The device was placed atop a steel tower in the Jornada del Muerto desert, which translates, with an irony that seems excessive in retrospect, as the journey of the dead man. The man who directed the scientific work of the project was J. Robert Oppenheimer. He had spent years working toward this moment, organizing the most concentrated collection of scientific talent in history toward a single goal. He was brilliant, driven, aware of the implications of what he was doing in ways that many of his colleagues were not, or chose not to be. When the device detonated, Oppenheimer watched from a bunker several miles away. The fireball rose. The shockwave followed. The desert was illuminated in a way it had never been illuminated before and has not been illuminated since. And in that moment, Oppenheimer recalled a line from the Bhagavad Gita, the ancient Hindu scripture he had read in the original Sanskrit. Now I am become death, the destroyer of worlds. What Oppenheimer was describing was not just the power of the weapon. He was describing a transition, a point at which a civilization's capabilities had crossed a threshold that could not be uncrossed, a point at which the knowledge of how to end civilization was permanently and irrevocably part of what civilization knew. Before Trinity, the destruction of human civilization was theoretically possible, but practically far beyond reach. After Trinity, it required only the decision of a small number of people. The gap between capability and catastrophe, which had always been measured in the vast logistical difficulty of conquering and destroying a global civilization through conventional means, collapsed overnight into a gap measured in minutes and megatons. That transition happened in 1945. We are still living in its consequences. Now, here is what the Great Filter adds to this picture. And this is the part that took me the longest to sit with clearly. We have spent time in this project, across the stories told in previous episodes, tracing the great catastrophes of this planet's history. The Great Dying, which killed 96% of marine species and nearly ended the experiment of complex life 252 million years ago. The Carnian Crisis, which dismantled the Triassic world and opened the door through which the dinosaurs walked. The Snowball Earth, which locked this planet in ice for tens of millions of years and forced life into the darkest margins of survival. In each of those stories, the filter was external, geological, astronomical, the crust of the Earth rupturing, the orbit of the planet shifting, the climate system tipping into a state that life had never encountered. In each of those stories, life was the victim of forces entirely outside itself. What the Great Filter hypothesis forces us to consider is something different in kind. What if the filter that waits ahead of every civilization is not geological? What if it is not external at all? What if the thing that almost every civilization cannot survive is the civilization itself? The technology that makes a civilization detectable across interstellar distances is the same technology that makes it capable of destroying itself. Nuclear energy and nuclear weapons are not separate discoveries that happen to share a word. They are the same discovery. The knowledge of how to split the atom does not come packaged with a lock that prevents the military application. It comes as a whole, and the civilization that develops it gets all of it, whether it is ready for all of it or not. The same is true, in different ways, of synthetic biology, of advanced artificial intelligence, of the class of technologies that give small numbers of actors the ability to cause damage at scales that were previously accessible only to states, and previously accessible only through the slow, expensive, logistically demanding process of conventional warfare. Each of these technologies follows the same pattern. The capability arrives before the wisdom to manage it. The power accumulates faster than the institutions, the norms, the collective agreements that would be required to ensure it is not used in ways that are catastrophic. Self-destruction is not the only possible future filter, and it would be a mistake to treat it as though it were. The barrier could be physical, a cosmic event of a kind we have not yet observed at close range. It could be economic, a ceiling on the resources available to support a civilization of a certain complexity. It could be social, a fragmentation that advanced technology makes worse rather than better. It could be something we have not yet imagined, a challenge that only becomes visible at a stage of development we have not reached. But self-destruction is the one we are forced to take most seriously right now, because it is the one for which we already have evidence in ourselves. We know we are capable of it. We have demonstrated that capability. The question is whether that capability is what ends us, or whether we are the rare case that learns to carry it without being destroyed by it. If civilizations routinely develop technology before developing the wisdom to manage it, and if that gap between capability and wisdom is wide enough and dangerous enough that most civilizations cannot cross it without catastrophic failure, then the galaxy should look exactly the way it does. Quiet, not because no one has ever been there, because almost no one has made it through. The civilizations that do not survive are probably not destroyed by asteroids or gamma-ray bursts. They are probably destroyed by themselves, by the gap between the pace at which they develop power and the pace at which they develop the capacity to handle it. We have been in that gap for at least 80 years. Since the morning in New Mexico, when the desert was lit from within by a fire that should not have existed, the question the Great Filter asks about us is not whether we are capable of destroying ourselves. We have already demonstrated that we are. The capability has existed since 1945 and has only grown since. The question is whether we are the rare exception, whether we are, somehow, the civilization that crosses the gap, that develops, in time, the wisdom that our intelligence has so far outpaced, that survives having the knowledge of how to end everything, long enough to reach the point where that knowledge is no longer the most dangerous thing about us. That is not a guaranteed outcome. It is not even, if the Great Filter hypothesis is correct, a likely one. But it is possible, and the word possible, in this context, carries a weight that deserves a moment. Possible means the outcome is not determined. It means that what we do, what we choose, what we build and what we refrain from building, what agreements we make and how faithfully we keep them, what values we embed in the systems that govern us, and what we do when those systems fail. All of it matters. Matters not just in the ordinary sense that choices have consequences. Matters in the specific sense that we may be, right now, in the part of the story where the outcome is still undecided. There is a concept in mathematics called a critical point. It is the place in a function where the behavior of the system is most sensitive to small changes. Near a critical point, a small push in one direction produces a very different outcome than a small push in the other direction. Far from the critical point, the system is relatively insensitive to small perturbations. Near it, everything matters. The next few centuries, possibly the next few decades, are the part of the story where the filter is either passed or not, where the civilization that built the radio telescope and the nuclear weapon and the genetic sequencer and the neural network either figures out how to carry all of that together into a future where it is not destroyed by any of it, or does not. The silence is not a sentence. It is a warning, and warnings are addressed to people who can still change what happens next. Chapter 5. The Mars Question. There is a rover on Mars right now. Not a metaphor. Not a thought experiment. A physical object. Roughly the size of a car. Powered by a radioisotope thermoelectric generator. Rolling across the floor of Jezero crater at a pace that a healthy human could outwalk without effort. It has been there since February of 2021. It has drilled into Martian rock. It has collected samples sealed in titanium tubes and left them in carefully documented locations on the surface for potential future return to Earth. It has taken hundreds of thousands of photographs. It has analyzed the chemical composition of rock and soil with instruments sensitive enough to detect organic molecules at concentrations of parts per billion. Its name is Perseverance. And every sample it collects, every rock it drills, every patch of ancient lakebed sediment it examines, is potentially the answer to a question that would change everything we think we know about the universe and our place in it. So far, Mars has given us hints, organics, ancient chemistry, candidate features that scientists take seriously and study with genuine care, but it has not given us confirmation. Nothing yet that forces the conclusion that life was there. Nothing that requires a biological explanation rather than a geological one. That absence, uncertain and incomplete as it still is, may be telling us something important, not in the way that absence of a disease is good news, where the absence is simply the neutral condition you were hoping for. Something more specific, more counterintuitive, more deeply unsettling, in a way that requires the previous chapter to understand fully. Let me build the argument from the beginning, because it deserves to be built carefully. Mars is not Earth. That is obvious. But what is less obvious, and what matters enormously for this argument, is that Mars and Earth share a history that makes them, in some respects, the most informative pair of worlds we have access to. Both formed approximately 4.6 billion years ago from the same disk of material surrounding the young sun. Both are rocky planets, both occupied, at various points in their early history, positions and conditions where liquid water was present on their surfaces. Mars, in its first billion years, had a thicker atmosphere than it has today. Temperatures that may have been above freezing, at least seasonally, and surface water in quantities sufficient to carve the valley networks and outflow channels that are still visible in orbital imagery. A world, in other words, that had the prerequisites for life as we understand it. Earth and Mars had similar early conditions. Earth produced life within a few 100 million years of those conditions existing. The question is whether Mars did the same. Here is why the answer matters so much. If life appeared on Mars independently of life on Earth, then we have two examples of life appearing under similar conditions, in a similar time frame. Two independent origins of life in one solar system. The statistical implication of that result is enormous. If life can appear twice in one solar system, it is almost certainly not rare in the universe. The conditions that produce life must be common, and the chemistry to biology transition. That step, whose probability we cannot estimate from a single example, must be something that happens readily when the right conditions are present. If life appeared independently on Mars, then the galaxy is very probably full of life. Simple life, microbial life, life that has not necessarily produced intelligence or technology, but life that is there, on billions of worlds, doing what life does. And if the galaxy is full of simple life, then the great filter, the bottleneck that explains the silence, cannot be in the early steps. The origin of life is not the rare part. Something else is. The filter is somewhere further along, perhaps at the step that produces complex multicellular organisms, perhaps at the step that produces intelligence, perhaps at the step that requires a technological civilization to survive its own capabilities. Perhaps, in other words, the filter is ahead of us, finding confirmed life on Mars, even the simplest possible life, even a fossilized microbial mat from 3 billion years ago that required an electron microscope and months of analysis to confirm, would be, under the specific logic of the great filter, one of the most unsettling discoveries humanity could make. Not because life on Mars is bad, because of what its independent emergence would tell us about where the filter sits. It would be evidence that the silence of the galaxy is not explained by the rarity of life, which means it must be explained by something else. And the something else that explains a galaxy apparently full of life, but empty of detectable civilizations, is something that ends civilizations. Every clean sample from Perseverance is, in this specific sense, a small gift. Every negative result is an argument, tentative and uncertain, but real, that we may have already passed the hardest part. This is not the only interpretation of the Mars evidence. The absence of confirmed life in the samples collected so far is not definitive. Mars is a large planet with a complex history, and Jezero crater is one location on one world whose subsurface has been barely touched by any instrument we have sent there. Life on Mars, if it ever existed, may have retreated to locations far from where Perseverance has searched, underground, near active geothermal areas, if any remain, in forms that our current instruments cannot detect or would not recognize. The hints Mars has given us, the organics, the ancient chemistry, the candidate features, are real and are taken seriously. They have not yet crossed the threshold into confirmation. That threshold matters. And until it is crossed, the honest position is that the question remains open in both directions. But the direction the evidence is pointing, tentatively and with all appropriate uncertainty, is toward a Mars that may have been habitable without having been inhabited, a world where the conditions for life were present, where some of the chemistry is suggestive, but where life itself, if it was ever there, has not yet shown its face clearly enough for science to confirm it. If that is what Mars ultimately turns out to be, then the origin of life is harder than the conditions for life. And if the origin of life is hard, then life is rare. And if life is rare, then the silence of the galaxy is less alarming than it would otherwise be, because it is explained by scarcity rather than catastrophe. There is a related argument that runs in the other direction, and it deserves to be stated plainly. If we are alone, or nearly alone, the implications are not simply comforting, they are also sobering in a different way. If there is no other life in the galaxy, or very little, then what happens here matters in a way that is almost impossible to hold in the mind without it feeling like too much weight. The history of life on Earth. 4 billion years. The bacteria and the stromatolites and the trilobites and the forests and the dinosaurs and the small mammals in the dark and the eventual emergence of something capable of sitting with this question. All of it is not one story among billions. It is the story, or one of a very small number of stories. Everything that has ever thought, or felt, or perceived, or wondered, may be concentrated on this one small world, around this one ordinary star, in this one unremarkable corner of one galaxy among 2 trillion. That is not a comfortable thought either. It is a different kind of uncomfortable. Not the discomfort of being threatened, but the discomfort of being unexpectedly and without preparation. Responsible for what? Exactly. For the continuation of the only story we know is being told. Perseverance is still rolling across Jezero crater. The samples are still being collected. The analysis is still ongoing. The question is still open. And every day it remains open is a day in which the answer is still possible in both directions. What perseverance is really asking, with the most precise instruments our civilization has yet built, is not whether Mars has interesting geology. It is asking whether we are alone, and the universe, through the hints that have not yet become confirmation, and the silence that has not yet been broken, is saying something back. The question is whether we are willing to hear what it is actually saying, rather than what we hoped it would say. Chapter 6. The Zoo of Silence. Everything in the previous chapters has proceeded from a single assumption so deeply embedded in the way we think about the Fermi paradox that it is easy to miss it entirely. The assumption is this: if intelligent civilizations exist elsewhere in the universe, they would behave, in at least some general respects, the way we behave. They would expand. They would explore. They would transmit. They would leave marks on their environments at scales that grow as their capabilities grow. They would, eventually, become visible. And the fact that they are not visible is therefore evidence either that they do not exist, or that something has prevented them from reaching the stage at which visibility would occur. That assumption is not obviously wrong. It is a reasonable starting point, but it is an assumption. And assumptions, when they are invisible, are where the most interesting mistakes hide. What if the silence is not telling us that no one is there? What if it is telling us that no one who is there is behaving the way we assumed they would? The explanations in this chapter are, by their nature, more speculative than what came before. The great filter is grounded in the mathematics of probability and in the observable fact of the silence. What follows is grounded in something different, in the logic of how minds behave, in the game theory of civilizations, in the possibility that we are not just missing signals, but missing the entire framework within which those signals would make sense. These are speculative arguments. Speculative does not mean unserious. Some of the most important questions admit only speculative answers, and refusing to engage with speculation in those domains is not rigor. It is intellectual cowardice dressed up as caution. Start with the simplest version of the idea that the silence is a choice. Imagine a civilization that is, by any reasonable measure, vastly more advanced than ours. A civilization that has been developing its science and technology for 1 million years, or 10 million, or 1 billion. A civilization that has solved, or at least navigated, the problems that may destroy us. That has survived whatever filters lay in its path and emerged on the other side with capabilities we cannot meaningfully imagine. What does that civilization want? we tend to assume the answer involves expansion, exploration, the colonization of star systems, the kind of outward-directed ambition that characterizes our own civilization at its most visionary moments. But that assumption is rooted in who we are right now. At this particular stage of our development, it is not obviously a universal feature of intelligence. Human ambitions have changed even across the short history of our own civilization. The impulse to conquer territory, which dominated the political history of most human societies for millennia, has not disappeared, but has changed its form in ways that would have been unrecognizable to a Roman emperor or a Mongol warlord. A civilization 1 billion years older than ours has had 1 billion years to evolve its ambitions, what it wants, and therefore what it does, may bear no resemblance to the outward expanding, signal broadcasting behavior that our models of advanced civilizations assume. This general idea has several specific versions, and each one is worth examining on its own terms. The first is what researchers call the zoo hypothesis, proposed formally by radio astronomer John Ball in 1973. It holds that advanced civilizations know we are here and have made a deliberate choice not to contact us. Not because contact is technically impossible, because contact is something they have considered and decided against. Perhaps they operate under something like a policy of non-interference, an agreement among advanced civilizations to allow younger ones to develop without external influence. Perhaps they regard contact as harmful to us, the way contact between technologically mismatched civilizations has historically been harmful to the less developed party. The zoo hypothesis is genuinely difficult to evaluate scientifically. We cannot distinguish between a universe in which advanced civilizations do not exist and a universe in which they exist but have agreed to observe us without making contact, because both universes look the same from our current position. Both are silent. What makes the zoo hypothesis interesting is not its scientific status, but what it implies about the nature of advanced intelligence. It implies that the outward expanding, resource-consuming, signal broadcasting model of civilizational development is a phase, a stage that civilizations pass through early in their development and eventually leave behind. Maturity may involve a kind of restraint that produces silence, a recognition that not every capability needs to be exercised. The second version is considerably darker and comes from a novel rather than a scientific paper. The Chinese science fiction writer Liu Cixin proposed what is now sometimes called the dark forest theory. The argument, stated as a logical proposition, goes like this. Every civilization in the universe faces two fundamental facts. First, resources are finite. Second, the intentions of other civilizations cannot be known with certainty. Given those two facts, and given that the stakes of miscalculating another civilization's intentions are potentially existential, a sufficiently rational civilization will conclude that the safest course of action toward any other civilization it discovers is elimination, not because it knows the other civilization is a threat, because it cannot know that it is not, and when the cost of being wrong is annihilation. The rational response to uncertainty is preemptive action. The result, if this logic applies to most civilizations, is a universe in which every civilization that becomes aware of another civilization's existence attempts to destroy it as quietly and quickly as possible, and in which every civilization that has survived to an advanced stage has learned, as a fundamental survival strategy, to make no detectable noise. The silence is not the silence of an empty forest. It is the silence of a forest full of hunters who have learned not to move. This theory has an implication worth stating plainly. If it is correct, then the signals we have been sending into space since the 1970s The Arecibo message. The content of the Voyager Golden Record. The continuous leakage of our radio and television broadcasts in an expanding sphere, now roughly 100 light-years in radius, may be among the most consequential things our civilization has ever done, reaching beyond our local neighborhood and announcing our presence to whatever is listening would be, in a dark forest universe, not an act of hopeful communication. It would be an act of profound and irreversible recklessness. The third alternative is the strangest, and in some ways the most hopeful. It was proposed by researcher John Smart and is called the transcension hypothesis. The argument begins with a question about the direction of civilizational development that is rarely examined. We assume that advanced civilizations expand outward, into space, into neighboring star systems. We assume the trajectory of development is one of increasing scale. But consider the trajectory of our own technological development over the past century. The most significant advances have not been advances in scale. They have been advances in miniaturization, in density. The computer that once occupied an entire room now fits in a pocket and is orders of magnitude more powerful. Smart argues that a sufficiently advanced civilization will follow this trajectory to its logical conclusion. Not outward into the physical universe, but inward into increasingly dense and efficient computational and experiential space. Not colonizing other star systems, but developing the internal complexity of their own information processing to a degree that makes external expansion largely irrelevant. Such a civilization has no large-scale fingerprints in the physical universe. Its presence is compressed. It is not absent. It is invisible to instruments calibrated for expansion. 3 different explanations. A choice not to contact. A universe in which contact is dangerous. A progression beyond the stage at which contact is something civilizations do. In all 3 cases, we are alone in a practical sense, not because no one exists, because no one is coming. Whatever needs to happen here, happens here. Whatever filters lie ahead of us, we navigate them without a guide who has been there before. A room can be silent because it is empty, or because everyone present has agreed not to speak, or has learned to communicate in frequencies we cannot hear, or has become something that no longer needs to fill a room at all. We know what the first kind of silence sounds like. We have spent 65 years listening for it and finding it everywhere. Whether the silence we are hearing is the first kind, or the second, is something we cannot determine from our current position. That uncertainty is not a comfortable place to stand, but it is an honest one. Chapter 7. The Silence as Mirror. There is a question that this story has been approaching from the beginning without asking directly. Not the question of where everybody is. That question has been with us since the lunch table in Los Alamos. Not the question of whether the filter is behind us or ahead. Not the question of whether the silence means absence or choice or something we do not yet have the conceptual vocabulary to name. The question underneath all of those questions, what does it mean to be here? In a universe that may be almost entirely empty of anything that knows it exists. Asking whether there is anyone else. The Fermi paradox. When you have followed it all the way to where it actually leads, stops being purely a scientific question and becomes something else. Something that touches the way you relate to your own existence, to the existence of the people around you, to the fact that any of this is happening at all. That transition is not a failure of rigor. It is what happens when you take a scientific question seriously enough to follow it all the way to its human consequences. Start with the simplest version of what the silence implies, and work outward from there. If the silence is real, and we have established that it is real in the specific sense of being a confirmed observational fact that has persisted across 75 years of increasingly sensitive listening. Then the universe is, at minimum, not densely populated with civilizations like ours. Whether it is completely empty of them, or sparsely populated, or populated in ways we cannot currently detect, it is not the crowded, communicating, interconnected, civilization-rich cosmos that the more optimistic readings of the Drake equation would suggest. We are, at minimum, rare. What rarity means. Not in the statistical sense we have been discussing throughout this story, but in the experiential sense. In the sense of what it is like to be a rare thing, in a universe that does not seem to know you are there, is a different question entirely. One that does not have equations. One that has only the fact of existence itself, which is the strangest fact there is, and which the silence of the universe makes stranger still. Consider what it would mean to confirm, definitively and beyond reasonable doubt, that we are alone, not probably alone, not apparently alone, given current search sensitivity, but alone in the strong sense that in the entire observable universe, across 2 trillion galaxies and more stars than there are grains of sand on every beach on Earth, the only thing that knows the universe exists is us. The only thing that has ever looked up at the night sky and wondered what was out there. The only thing that has ever built an instrument to listen, or sent a signal outward, or asked the question that Fermi asked at that lunch table in 1950. The only thing that has ever experienced anything at all, in the sense of having an inner life, a perspective, a sense of what it is like to be something rather than nothing. If that is true, then the universe is not a stage on which many dramas are being played simultaneously. It is a stage on which one drama is being played. One story. Ours. Everything else. The galaxies and the superclusters and the vast dark stretches of intergalactic space and the billions of years before Earth existed and the billions of years that will follow after the sun has consumed it. All of it is context. The material conditions within which this one improbable story is unfolding. That thought can collapse in 2 directions. The grandiosity version says, we are special. We are the point of it all. The universe made itself in order to be known by us. The despair version says, if we are alone, nothing matters. The universe will continue after we are gone, indifferent to our absence. And the whole enterprise of civilization amounts to nothing more than a brief anomaly in the thermal history of a minor planet. Neither version holds up. The grandiosity version fails because the universe did not make itself in order to do anything. It does not have intentions. It is a physical system operating according to laws that are indifferent to the existence of anything that can observe them. We are not the point of the universe. We are an outcome of it. The despair version fails because it rests on a conception of mattering that is mistaken. It assumes that significance requires an external witness, that things matter only if they matter to something outside themselves, that the universe has to care about us for us to be worth caring about. Significance is not something conferred from outside. It is something that arises within a system capable of recognizing it. We are capable of recognizing it. The love between 2 people does not require a cosmic audience to be real. The achievement of understanding something true about the universe does not become meaningless if the universe does not notice. The experience of being alive, of perceiving and thinking and feeling, is not rendered empty by the indifference of the physical laws that produced it. We are the ones who decide what matters, not because we invented the concept of mattering out of nothing, but because we are, as far as we can tell, the only things in the observable universe that have the capacity to do that deciding. Now, take this one step further. Because the silence asks us to, if we are alone, or nearly alone, or rare enough that the distinction barely matters in practical terms, then the continuation of what we are is not just a matter of human preference. It is the continuation of the only process in the observable universe that generates understanding, perspective, experience, meaning, everything that has ever been thought, felt, perceived, or known happened here, on this planet, in the minds of living things that are connected by an unbroken chain of generations to the first cells that appeared in ancient seas 3.8 billion years ago. If that chain breaks, the universe does not lose one civilization among many. It loses the only thing it has, as far as we know, that gives it the capacity to be known at all. The silence should not make us feel important. The universe assigns importance to nothing. It should make us feel responsible. Responsible in the sense of being the current custodians of something that cannot be replaced if it is lost, because there is no one else to replace it. The physicist David Deutsch has argued that all problems are, in principle, soluble. Not that we will necessarily solve them, that there is no physical law that prevents their solution. The failures of civilizations are not inevitable in the way that the cooling of the universe is inevitable. They are failures of knowledge and of will, things that could in principle have been otherwise. The problems we face are not solved yet. They are also not unsolvable. There is no physical barrier between where we are and where we need to be. There is only the gap between what we know and what we need to know, between what we are willing to do and what needs to be done, between the pace of our technology and the pace of our wisdom. That gap is closable, not easily, not without difficulty and failure, and the kind of sustained collective commitment that human beings have historically found extremely difficult to maintain. But closable. The silence does not tell us we will close it. It tells us that almost no one does. Those are different statements. The first is a prediction about our future. The second is a statistical fact about a class of entities of which we are a member. The statistical fact is alarming. The prediction is still open. We are, if the great filter lies ahead, at the place in the story where most stories end. Not because ending is inevitable, because the forces that end stories are real and present and have ended almost every story that has reached this point. There is a question worth asking before this chapter closes, one that connects everything that came before it. If there is a civilization somewhere in this galaxy that has been receiving the sphere of electromagnetic noise we have been broadcasting since the early 20th century, what have they heard? They have heard our wars. The radio transmissions of the Second World War, if received by a civilization 60 or 70 light years away, are arriving about now. The signals carrying information about what human beings are capable of doing to each other are out there, moving through space at the speed of light toward whatever is listening. They have also heard our music, our stories, the accumulated electromagnetic record of a civilization that, alongside its capacity for destruction, has produced works of extraordinary beauty and made discoveries of extraordinary depth, has learned to read the history of matter from the first moments after the beginning to the present, and found in that history something that feels like meaning. They have heard both, because we are both. The question of which one defines us is not a question the universe answers. It is a question we answer every day. In the sum of the choices that people and institutions and societies make about what they build and what they refrain from building, what they protect and what they allow to erode, what kind of future they are trying to reach, and how seriously they take the work of getting there. That is the mirror. The silence holds it up not to judge. The universe does not judge, but to make visible what is there, to show us what we are, and to leave open without resolving. The question of what we might yet become. Go back to the lunch table. Los Alamos, New Mexico. The summer of 1950. The cafeteria is ordinary in the way that cafeterias are ordinary everywhere. The smell of food, the sound of conversation, the particular quality of light through institutional windows in the middle of the day. The men at the table are not ordinary, not by any reasonable measure, but they are doing what ordinary people do at lunch, talking about nothing in particular, letting the conversation drift. Enrico Fermi is 50 years old. He has already done the work that will define his legacy. He has stood in a squash court beneath the stands of a football stadium at the University of Chicago on December 2nd, 1942, and watched a chain reaction sustain itself for the first time in history. He has contributed to the project that produced the weapon that ended the war in the Pacific and began an era that humanity is still navigating. He is sitting at a lunch table, talking about flying saucers in a newspaper cartoon. Something in the conversation triggers a thought he has probably had before in some form. He laughs. He asks the question, "But where is everybody?" His colleagues understand immediately. The universe, the hundreds of billions of stars, the billions of years the whole enterprise has been running. Given all of that time and all of that space and all of those chances, where are they? The conversation moved on. Lunch ended. The men went back to their work. Fermi died 4 years later, at 53, before the systematic search for extraterrestrial intelligence had even begun. He never knew whether the question had an answer. Neither do we. That is where we are. 75 years after the lunch table, not closer to an answer in any definitive sense. Though we are closer to understanding the shape of the question, we know that planets are common, with thousands confirmed and evidence suggesting they exist around virtually every star in the galaxy. We know more about the chemistry of life and the conditions that might support it. We have built instruments of extraordinary sensitivity and pointed them at the sky for decades. We have developed theoretical frameworks that give the silence a structure it did not have when Fermi asked his question. We have not found anyone. What the silence tells us, honestly and without embellishment, is this: the universe is at least not densely populated with civilizations that behave the way we assumed they would. The signal we have been waiting for has not arrived in 75 years of listening. The galaxy does not appear to have been significantly modified by the engineering of advanced civilizations. Mars has offered hints, but not confirmation. The numbers that should guarantee the existence of thousands of civilizations are being counteracted by something we do not yet understand. That is what the silence tells us. Not what it means, what it tells us. The meaning is a different question. And meaning, unlike signal detection, is something we construct rather than discover. The universe does not provide meaning. It provides facts. What we do with those facts, the frameworks we build around them, the implications we draw, the way they change how we live and what we care about, that is something we make out of who we are and what we value and what kind of future we are trying to reach. The silence is not proof that we are alone. It is proof that survival may be much harder than intelligence. That sentence has been the backbone of this story, and it is worth sitting with one final time, because it contains more than it initially appears to. Survival being harder than intelligence means the thing we are most proud of: our minds, our science, our technology, our capacity to understand the universe and act on that understanding is not sufficient. It is necessary. It got us here, but it is not enough to get us through. Intelligence without wisdom is precisely what the great filter if it lies ahead, would select against. A civilization smart enough to build the weapons, but not wise enough to decide not to use them. Smart enough to alter the climate, but not wise enough to stop before the alteration becomes irreversible. Smart enough to create systems of extraordinary power, but not wise enough to ensure those systems remain aligned with human flourishing. Smart enough, but not wise enough. That gap between smart enough and wise enough is the gap that the silence may be measuring. The gap that we are currently living inside, with all its uncertainty and all its danger and all its possibility. Possibility is the word worth ending with, not because it is comforting, though it is, but because it is what is actually true. The outcome is not determined. The filter, if it lies ahead, has not yet closed around us. The silence is not a sentence. It is a warning, and warnings are addressed to people who can still change what happens next. We can still change what happens next. Not easily, not without difficulty and failure and sustained effort. But the physics does not forbid it. The history does not preclude it. The silence does not predict it. The silence predicts what happens to civilizations in aggregate. But aggregates are made of individual cases. Some civilizations, perhaps, beat the odds. Some fraction of the things that almost never happen do happen. Because almost never is not never. And probability is not destiny. We could be that fraction. Whether we are depends on things being decided now. In laboratories and legislatures and living rooms, in the choices that people and institutions make about what they build and what they restrain, what they protect and what they allow to erode, what they are willing to sacrifice in the short term for the sake of a long term they will not personally live to see. In the choice to take the warning seriously, rather than looking away, in the choice to close the gap between smart enough and wise enough, even though the gap is wide and the time may be short and the forces pulling in the other direction are powerful and sometimes feel overwhelming. In the choice to be against the odds and against the apparent precedent of the silence. The exception. Fermi asked where everybody is. The honest answer is that we do not know. The silence is real, but its explanation is uncertain. The universe may be empty or may be full in ways we cannot yet detect. And the difference matters enormously for how we understand our situation and our responsibilities. But the more important question, the one the silence is actually asking, is not where everybody is. It is whether we intend to still be here, not in the trivial sense of surviving another year, in the deep sense, the sense that involves a civilization that has understood its own fragility and decided to take that fragility seriously. That has closed enough of the gap between smart enough and wise enough to navigate what lies ahead without being destroyed by what it has built. That question will not be answered at a lunch table. It will not be answered by a radio telescope receiving a signal from across the galaxy. Though that signal, if it came, would tell us something important about whether the filter is behind us. It will be answered by the accumulation of choices made by people who understood what was at stake and chose, in the face of that understanding, to act accordingly. Those choices are happening now on one small planet, around one ordinary star, in one unremarkable corner of one galaxy among 2 trillion. Something has spent 75 years listening for an answer that has not come. And in the silence between the transmissions, in the space between the signal we keep sending and the response we keep not receiving, there is a question that was never really about the universe at all. It was always about us, what we are, what we are capable of becoming, and whether we will still be here. In the long and uncertain future that the silence leaves open. To find out, the universe has not answered yet. The question is whether we will